You know those incredible crystal clear images of Earth from space we see all the time? Well, it turns out they don't start out that way, not even close. Today, we're going to take a look at the secret journey of a satellite image, how it goes from being this messy, raw signal into a pristine piece of scientific truth. I love this quote from the source material because it really gets to the heart of what this is all about. This whole process, it's not just about making a pretty picture. It's about building a solid, reliable bridge from raw, messy data to real, actual knowledge about our planet. So that's the big question, right? How in the world do scientists take this noisy, warped signal from a satellite that's hundreds of miles up and turn it into something we can actually trust, something we can measure? Well, that whole journey, it all starts with a single, very messy pixel. So let's start there. All right, first things first, we have to understand what we're starting with. And trust me, it is not much to look at. See, the raw data that gets beamed down from a satellite, it's not really an image yet. It's just a long stream of what are called digital numbers, or DNs. And these numbers are a complete mess, just corrupted by everything you can imagine, from the satellite's own sensor glitches to the very air that the signal had to punch through to get to us. So the very first step on this journey is basically a massive cleanup operation. We have to correct for the physics of light itself, and then for all the distortions caused by our own atmosphere. And this first big process is called radiometric correction. The best way to think about it is like tuning an instrument. You know, every single sensor on a satellite has its own little quirks and flaws. This step makes sure we account for all of them, so the data is consistent and, most importantly, reliable. And what's really fascinating here is that satellites aren't perfect forever. Just like any piece of tech, their detectors get old. They can start to lose sensitivity over their lifespan, and that can introduce some really weird errors, like visible striping across an image where one detector isn't performing quite like the one next to it. And this slide right here shows you exactly what I'm talking about. On the left, in that uncalibrated data, you can see that distracting striping. But what's even more important is that you can't compare a pixel from 2013 to one from 2024 because the sensor itself has changed. But look at the right. After calibration, the image is clean. And this is the whole point. This step is what makes the data scientifically useful for long-term studies, like tracking deforestation over decades. It's absolutely crucial. Okay, so the sensor's been corrected, but that signal still had to travel through miles and miles of air. And as sunlight bounces around off molecules in the air, it creates this kind of haze, especially in the blue part of the spectrum. It's kind of like trying to take a picture through a slightly dirty window. But scientists have a really clever and surprisingly simple way to digitally clean that window. It's called dark object subtraction. The logic is so cool. They find things in the image that should be almost perfectly black. Think the shadow of a big mountain or super deep, clear water. In the raw data, those things aren't black. They have a little bit of brightness. And guess what? That brightness is the haze. So they just measure that value and subtract it from every single pixel in the entire image. And just like that, the window is clean. So now our pixels have the right color, but they're not in the right place. We've got a clean picture, but we don't really have a map. Not yet. This is where geometric correction comes in. This is the part of the process where we take that floating image and we pin it down to its exact location on Earth. This is what lets you overlay a satellite image on Google Maps or see your GPS track on top of it. Without this step, it's just a pretty picture. With this step, it becomes a map. And the level of accuracy they're going for is just staggering. A really well-corrected image has a geometric error of less than 1 pixel. So to put that into perspective, if 1 pixel in a Landsat image represents a 30-meter square on the ground, that means every point in that image is placed, on average, within that 30-meter square of its true location. It's an incredible level of precision. But of course, there's a catch. The Earth isn't flat. And when a satellite looks down at, say, a mountain, the peak of that mountain is physically closer to the sensor than the valley next to it. This can make the whole mountain look like it's leaning or tilting away from the satellite, which totally messes up distances and shapes. So, the solution is this amazing process called orthorectification. What scientists do is use a 3D map of the Earth's surface, that's the digital elevation model, to mathematically correct for all those terrain distortions. It's like they digitally drape the image over that 3D model, which removes the tilt. And the result is an image where you can finally measure distance and area accurately, even on the steepest mountain slopes. Okay, we've cleaned the pixel values and we've put them in the right place on the map. Now it's time for the final assembly line, where we combine all these corrected images into something truly powerful. But first, we have to deal with the ultimate enemy of any satellite image, clouds. And we also have to deal with their sneaky sidekick, shadows. Shadows are actually a huge problem because their dark signature can look a lot like water to a computer, and that can lead to some major mistakes. Thankfully, modern satellite data comes with these things called quality assurance bands, which acts like a little label for every single pixel, marking it as cloud, shadow, or clear. This lets algorithms automatically know which pixels to just ignore. And once we know where all the bad data is, well, that's when we can perform some real magic. This quote just captures it perfectly. By combining multiple images of the same place over time, we can essentially erase the clouds from existence. There are two key ways this gets done. The first is mosaicing. Think of that as being all about space. You're stitching together images that are right next to each other to create one giant, seamless map. The other is compositing, and that's all about time. You're stacking images of the exact same location from different days. Then an algorithm can just look through the stack for each pixel and pick the best, clearest, cloud-free view, giving us a perfect, continuous picture of the world. So, after all of that, the radiometric correction, the atmospheric correction, the geometric correction, plus all the masking and compositing, what are we left with? We have something incredibly valuable. It's called Analysis-Ready Data, or ARD for short. This is it. It's the final, perfected product. That bridge has been crossed. This is data where all of that incredibly hard work, all that heavy lifting, has already been done for us. It frees up scientists to stop cleaning data and to start actually focusing on what the data tells us, to focus on the science. And really, that's the whole point of this entire journey, isn't it? From a noisy, messy signal to a perfect, measurable map, every single step is designed to create this reliable foundation for discovery. And that leaves us with the most important question of all. With this incredible power at our fingertips, what truths about our planet are we going to choose to uncover?